So during this session, I am going to discuss a few numerical say the problems and how to determine the number of Kanmans when the probabilistic model is applicable. Now we have already explained that what is a Kanban systems and the working of a typical Kanban systems using the two Kanban cards. We have already explained, in fact. So the working is known to you. Now but the understanding of the working of a Kanban system will be better if we take off a few numerical examples, and these examples are very common. And right at this point in time, we have also referred to the deterministic model for the number of Kanbans, and this number of Kanbans to be used in a particular say the production system or the pool system is a very important the parameter. Now let us first talk about the first numerical example. Consider the production of a certain item manufactured in XYZ company. Its requirements are 10,000 units per month. If you refer to the discussions in the previous the lecture sessions, you might have noticed that we have mentioned that the average demand is to be known, and initially we do not consider the demand to be a variable. Is it okay? So the 10,000 units per month is considered to be the average demand. We are not say the considering the standard deviation of the demand. Suppose the company has just started implementing the JIT systems. That means essentially it was initially a push systems, and because of the erratic the demand pattern situations the company the coming across, so it tries to it changes its systems from the push to pull. Accordingly, the policy variable is set at alpha equals to 0.4. That means still the company feels that that there is a significant or the strong effect of the external the factors on the performance of its inventory and production control system. So that's why the value of alpha is considered as high as 0.4. The container capacity is fixed at 50 items or the 50 units. It could be either 50 or 100, and the production lead time is half a day. Now the question is determine the number of production Kanbans. Suppose the company has stable production environment. That means it is initially it was unstable. That's why the value of alpha was 0.4. So now by taking some effective measures, the company has reached a stable condition. So it is able to create a stable production environment, and the policy variable can be fixed at alpha equals to 0.00. It will have a direct say the impact on the safety factor, determine the number of Kanbans and the resulting impact on work in process inventory. So while we determine the number of the Kanbans, obviously till now we have learned the deterministic model, so we will apply that deterministic model only. And this particular the kind of the formula which we will be using to determine the number of Kanbans, this formula has been was developed by Toyota many years back. Now the third question is, what happens if the lead time is increased to 1 day? It was half a day, so now it has become 1 day, whatever may be the reasons, because the labor shortages and failure of machines. So there could be many reasons that why so the lead time may increase. So you have come to know that there are two specific reasons. One is the shortage of labor or the workers, and the second reason could be, possible reasons could be, the machine failure. Now you start thinking about other possible reasons. These are the two specific say the just examples, but you should also be aware of that how many what are the specific reasons, the set of reasons for increasing or increased the lead time. What happens if the lead time is reduced to 0.25 days because of process improvements? So this is at the other extreme. The value of alpha is 0.30 as a result of these process improvements. So there is a relationship between say the safety factor and say the safety factors and the lead time. Is it okay? So the three important factors, so the four important factors you need to consider to determine the number of say the Kanbans, and what we are assuming that these three factors or these four factors are interrelated. So what is the solution? So the number of Kanbans is given by the daily demand, then the lead time, and this is the safety factor. So in the formula which you have used, you have referred to, so the notation we have used, that is capital D. The lead time has got the two parts, TW and TP. So both are added, so you get the lead time, and the safety factor is specified as 1 plus alpha, and the container capacity, the notation is small a. Now assuming 20 work days in a month, the daily demand is 10,000 divided by 20. Now this is your assumptions. There could be 24 days or 25 days, but you have to specify what is your assumption. That means what you try to do, that means already I have mentioned that the JIT systems, or for that matter the Kanban system, is used for the short term planning and control purposes, and so the day wise you try to control, you try to monitor the inventory as well as the production control situations. So here, so you need to know the daily demand. So it is 10,000 divided by 20, that is the 500 units. And so what is the number of Kanban? That means that this is 500, this is lead time is half a day, and the safety factor is alpha, so that's why it is 1.40, and the container capacity is 50 units, so this number is 7. Next is, if alpha equals to 0, that means there is no impact of the external factor, and that's why it is an 100% the stable system. So so the safety factor becomes 1. Accordingly, the number of Kanbans is 500 into 0.5 into 1 divided by 50. So it is reduced to 5. And in the third the case, the number of Kanbans is 500, that is the daily demand, and this the lead time becomes 1 day, and your safety factor remains at 1 because alpha value is 0, and container capacity remains same, that is 50. So this becomes 14. So the number of Kanbans become 14. The implication of this change in the system operation is that the average inventory increases by 350 units. That means it was initially it was 7, so now it has become 14. So there is an increment of the 7 say the containers, and each container the contains 50 units. So so this increase is 350 units compared with case 1. This is because extra containers are available as safety stock. Okay, so this is because what is important is initially it was 0.5, now it has become 1. So these also is also affecting the number of Kanbans and the average inventory. In the fourth case, the number of Kanbans is 500. The lead time is reduced to 0.25, and but the alpha value is now assumed to be 0.3. That means some disturbances you are getting from the external sources. Container capacity remains same, so it becomes 3.25. So the 3.25 you change it to say 4. Okay. So now you can manage the situation. You can control the situation with say the 4 containers. Okay, or number of containers becomes 4 Kanbans. Now, so the next example, that is the numerical example 2. Let us discuss the next example. Consider the manufacturing of product Z in a company. Product J is assembled from 2 parts, X and Y. Okay, a very simple case we are considering, just to understand the concept clearly. Now this the 2 parts are manufactured in the company. That means there is an assembly operation, there is also a manufacturing operation. And what is important is, in any GIT based production systems or inventory control systems, you must try to create a conditions where there is a perfect match between, or perfect balance between, the part manufacturing and the assembly. Normally this is not the case in a push system. In the pull system, what you try to do, that means you try to synchronize the operations of the part manufacturing with the operations of the assembly. So there must be a perfect matching. There are many instances where these conditions the company could achieve by implementing GIT based production system. So a schematic layout depicting preceding stage, the stacking area, subsequent stage, and the flow of production and withdrawal Kanbans is given in the figure. So we will show you the figure. The data given in the table are available. That means those data also you will come to know. And with those the data, you need to determine the number of withdrawal and production Kanbans. Now, in the next condition which you face, that is, suppose the assembly process is shifted to another country, say Mexico, as a part of reorganization. Okay. That means you will be doing your manufacturing activities at your plant, but the assembly operation now it will be done in another plant as located in another country, in a foreign country. The lead time to travel between the new location in Mexico and the present plant location is 4 days each for parts X and Y. Is it okay? Because the parts X and Y they are sent in the same lot. Determine the number of withdrawal and the production Kanbans and the impact of this policy on work in process inventory. So this is the system. That means you have the work center for manufacturing part X, you have work center Y for manufacturing part Y, and what is PKX? This is the production Kanban for the X item, and this is the production Kanban for the Y item. So now this is the stacking area. So the production Kanban moves to the stacking area with the container, and then you get say this is the withdrawal Kanban for the X unit, and whenever you get the withdrawal Kanban, that means from the stacking area this container moves to the subsequent process. So, and again this is the empty container, and it comes to the stacking area, and subsequently with the say the production it goes to the work center X. Is it okay? And what is Z? Z is the assembly center where both the units, that is both the parts X and Y are used, and as per the bill of material or the product structure, you are already aware of what is the product structure code, what is the product structure records. So as per the bill of material, so you know what is the sequence of say the operations or say what the process you will adopt for doing the assembly, which part comes first, which part comes next. So all these details are known, and then you carry out the assembly activity. So PKX is production Kanban for part X, PK say Y production Kanban for part Y, WKX is the withdrawal Kanban for part X, and WKY is the withdrawal Kanban for part Y. SAX equal to stacking area for part X, and SAY is the stacking area for say the part Y. Okay. Now with this, now this is the data available. That means for part X and Y, demand in units per day, it's 2000 units. This is 800 units. The lead time values are given. That is for part X it is 1, and for part Y it is 0.5 days. This is at the assembly stage, and the value of alpha, the safety factor related, the value of alpha is 0.00, and this value is 0.25, and the container capacity for X is 100 and for Y it is 50. So this is at the assembly stage, and for the manufacturing stage, this is 2000, this is 800, they remain same, but the lead time at the manufacturing stage it is 0.5 day, and for Y it is 1 day, and value of alpha is 0.2 for part X, that means the manufacturing area X, and for manufacturing area Y the value of alpha is 0, and the container capacity for manufacturing area X is 100, and for manufacturing area Y it is just 50. So with this data, so you apply that formula. Now this is the assignment given to you, and you just find out that X will be 20 and Y equals to 10, X will be 12 and Y equals to 60. That means withdrawal Kanban and the production Kanban. Okay, so first you determine the number of withdrawal Kanbans, okay, by applying the formula, that deterministic model, and then you use the same say the model, okay, same formula to determine the production Kanban. So the part 1 will have two sections. The first section relates to say withdrawal Kanban determination, and the part B relates to the production Kanban, so the number of production Kanban determination. Since the lead time is now 4 days, the number of withdrawal Kanbans for parts X and Y are 80 and 80 respectively. So you need to calculate again when you change the lead time. So only the same formula you will be using, but you change the value of the lead time. The impact of this decision is that 60 containers per part X and 70 containers per part Y remain in the pipeline. Initially it was 20, now it has become 80 for part X. So 60 more the containers you require, okay, for part X. Now initially it was the 10 for part Y withdrawal Kanbans, and now it has become say 80, so the difference is 70. So 70 containers for part Y remain in the pipeline. There is no change in the number of production Kanbans. It is obvious in fact. So this is just an illustrative example so that you understand this particular formula. This is deterministic the model fully, and there is there is a perfect understanding that why, how the factors are affecting say one another. Now the next important the model you may use for determination of number of Kanbans is the probabilistic model. So how to say get this probabilistic model? In a JIT system, usually planning horizon is 1 month. Please make a note. MPS is frozen for 1 month only, and the number of Kanbans at a work center is determined based on average demand for the period. The lead time is one of the factors determining the number of Kanbans. I've already, if you look at the formula you use for determination of number of Kanbans, so lead time is mentioned as one of the important factors. However, the lead time may be a variable, and hence there may be variations in the demand during lead time. So for determination of the number of Kanbans in this context, that means the probabilistic model, we assume that the probability mass function PMF of the number of Kanbans is known. This is some standard method you may use. You refer to any so the good textbooks on probability and statistics. So definitely you will know, or you will get some standard methods to determine the probability mass functions for the number of Kanbans. It is a discrete random variable. Holding cost per container per unit time is known. So this the estimate you must have. Similarly, the shortage cost per container short per unit time is also known, that is CS. So these two notations we have used. At any point in time, let there be n number of Kanbans in the system. Okay. So if the actual requirement for the Kanban is X, there is n number of Kanbans in the system, but the actual requirement may vary. So it depends on what sort of the demands imposed on you and what is the lead time. So a number of factors actually may determine the actual requirements during a particular say the time period. Now there may be two possibilities. So actual number, the circulating within the system, that is n number of Kanbans. Your system is having n number of Kanbans where your actual requirement is X. So there could be two cases when X could be less than n. That means your actual requirement is less than what is available. So obviously there will be holding cost, and what is the expression for expected holding cost? That is the per unit, it is CH. Okay, already you have this estimate into sigma n minus x to px, and x varies from 0 to n. Is it okay? A simple logic. So x varies from 0 to n, and in the case 2, when x is greater than n, so now you will have the expected the shortage cost, and the expected shortage cost is CS into sigma x minus n into px, and x is varies from n plus 1 to infinity. So you have the expected holding cost, and you have also expected say the shortage cost. So these two expressions you have, and then what is the total expected cost? That means when you add these two costs, that means expected holding cost and expected shortage cost. So you get this total, the cost total expected for when there are n number of Kanbans in the system. That is, if you add these two costs, this part is basically the holding cost, expected holding cost, and this is the expected number of units actually you are for which the holding cost is applicable, and this is the expected number of so the unit short, and the per unit short you are incurring a cost of CS. So you have these expressions. Now for determining optimal value of n, the minimum, the total cost satisfies the following conditions. Is it okay? This is the standard procedure we employ for determining say the optimal value of so the n in a discrete case. So the delta TCN is TCN plus 1 minus TCN. So this must be greater than 0. And delta TCN minus 1, that means TCN minus TCN minus 1 is less than 0. Okay, that means for n plus 1, you will incur a cost which is greater than the cost you incur with n, and similarly with n minus 1, the cost you incur should be greater than the cost you incur with n number of Kanbans. So this is the logic you put forth. Taking first forward difference and simplifying, we get these expressions. Okay, so this is capital Pn greater than Cs by Ch plus Cs, and this capital Pn is equals to actually sigma Px, x varies from 0 to infinity. That means it is basically the cumulative distribution function of x. Taking the first backward difference simplifying, we get capital Pn minus 1 is less than Cs by Ch plus Cs. Okay, and obviously this is the capital Pn minus 1 is sigma Px, x equals to 0 to n minus 1. So the optimal number of Kanbans can be determined from the following expression. So the capital Pn minus 1 less than Cs by Ch plus Cs less than capital Pn. Okay, so this is very the simple expression. So you have to use these inequality expressions to determine the number of n. So what we have mentioned that we have considered the Kanban system, and the Kanban systems lies at the heart of the JIT based production system, and the main purpose of the Kanban system is to control the inventory level, as well as it also controls the flow of inventory or the flow of materials in a production systems. And in order to say establish these Kanban systems, what you need to do, you must know how to determine the number of Kanbans, for which the two models we have referred to. The first model is very simple. It is called deterministic model. In majority of the cases, what the Toyota has observed, that the deterministic model will be very effective, whereas in certain other cases where you may not have sufficient control on your production systems, and the variability has to be allowed, or the variations in the production system has to be allowed, and you try to fine tune your the number of Kanbans with the variable demand, then so you have no other options but to go for using the probabilistic model. So both the cases we have discussed, and the other issues we will be discussing in the subsequent lecture sessions. Thank you.